All right, hi everyone. We'll get started. I'm just gonna sign into Zoom on my iPad. Um, Welcome to today. This will be the second review set or second to last review session that I do. So before we get started, I just wanted to ask for a review session on Sunday, since that's before your final. Would you like a final review earlier in the day, or like how I've been doing last minute around 6 or 7 o'clock to ask final questions? I'm up to either. I can either do like mid-morning, early afternoon, or I can do like 6, 7 on Sunday. Is there a preference for a time? Okay, okay, that's fine. I can do earlier in the day. Um, it'll be recorded, so I will, if you can't make it earlier in the day, then you can just watch it later at night. So I'll probably plan for that around like 1, because that be somewhere at 3. So plan on like 1-ish for that one, and then I'll record it and post it, and that'll be like the last little bit that we do. Alrighty. Let me join Zoom from my iPad. So in the meantime, is there anything that we would like to go over today? Since the mock exam came out, I'm assuming people are gonna have questions on the mock exam, but I'm happy to go over just like general content as well if there's topics that you don't have a firm grasp on and you would like to just go over general overview of stuff as well. Or any previous quiz questions, any previous exam questions, we can do anything you want for this hour. Anything in particular we want to see? Yeah, absolutely. Alrighty. Let's do this one. Alrighty, so let's look at this question here. We have a 1 liter solution of 0.5 molar HNO2, which has a Ka of 4.0 times 10 to the negative 4. And we're being titrated with 0.5 molar NaOH, and we want to know what is the pH of the solution after 250 milliliters of 0.50 molar NaOH have been added. Okay, so does anyone know where we're going to start with this question? What we need to look at first, or what we need to figure out in order to get started? Yeah, perfect. So we need to convert to moles because we need to figure out where in our titration we are. We have a, what is the classification of HNO2? What do we call that in terms of weak, strong, acid, or base? Good, so this is a weak acid, and we are titrating with what? What is our NaOH? Good, this is a strong base, perfect, right? So we have a weak acid, strong base. We need to figure out which one we have excess of, if we have excess. So we convert to moles by taking 1 liter, multiplying that by 0.5. So we end up with 0.50 moles of HNO2. And then we have 250 or 0.250 liters multiplied by 0.5 molar. So we get 0.125 moles of NaOH. Okay, once we have our moles, what is the next thing we need to do? Yep, so you can do an ICF table, or you can just say which one is limiting and go from there. But right, the big thing to tell you after you find moles is that you're comparing your moles of your acid to your base. You have a limiting reagent of your sodium hydroxide, and you have excess of HNO2. So you have more of your weak acid than your strong base. So those will be used up together. Those will be used up in order to create your products. You will use up all of your sodium hydroxide in a 1-to-1 ratio to your HNO2. So after this becomes 0.375 moles HNO2 remaining, and this becomes none remaining, right? Right, so we just have HNO2 left in our solution after we added our titration or our titrant. Okay, so then this turns into an ICF table because we'll have HNO2 and water forming, what is our conjugate base of HNO2? Perfect. We'll have NO2 minus and H3O plus. Right, and remember we're working with a weak acid, so we should be forming that H plus or that H3O plus ion in our product side because we want that acidic portion of our titration. So once we have this, what are we plugging in for the initial concentration of HNO2? Good, yep. So we can use 0.375 moles. I'm gonna make sure that we write that it's moles here. We can use this directly because what equation are we eventually going to use? Good, we will eventually use the Henderson-Hasselbalch equation. That will result in us dividing our base by our acid. So if we change our moles to concentration, the concentration units would actually give you the same answer as if you just used the molar units. So in this scenario, you don't necessarily have to convert back into molarity. You can keep it as just moles. However, if you are looking at the equivalence point or you're looking at after the equivalence point, then the concentration really matters. So if it's going to screw you up to only know of a certain occasion where you can or cannot convert back into molarity, just always convert back into molarity. In this case, you can stay in moles. But I'm just going to note that it is moles and you should be using molarity, but it'll give you the same answer. So in this case, we'll have 0.375 moles, and what is our initial concentration for the other portions or the other components in our reaction? Do we care about water? No. What about NO2 minus? It's not going to be 0 for NO2 minus. We do know how much NO2 minus was formed. How do we know how much NO2 minus was formed? Yeah, Alexis, that's it. Yep. We're going to take the limiting reagent, and whatever was used up there was converted into the number of moles of our conjugate base, right? Because when we used up HNO2 and NaOH, when those combined together, it formed some NO2 minus. So that'll be kept there. And we only are forming water, so we actually don't care about our H3O our H3O plus when we are talking about our buffer situation. So we don't need to worry about that one, especially because we're using the Henderson-Hasselbalch equation. H3O plus doesn't come up. So we'll take pH is equal to pKa plus the log of base over acid. And we'll see that pH is equal to the negative log of our Ka. And we'll have the log of our base, which is 0.125, of our acid, which is 0.375. So I've got a pH of 2.92. Okay, do we agree or disagree on this one? Okay, so when we look at this portion of our titration, we started off with a weak acid and a strong base, and we compared the number of moles of acid to base. right? We're just looking at acid and base, doesn't really matter if we are talking about a strong acid, weak acid, whatever. We're just comparing acid to base, and we see that our base is in excess, or sorry, is in limiting reagent, our weak acid is in excess. So this means that after we use up all of our base, that means we're going to have some molarity or some moles of weak acid that is left over. That will be in solution, right? This 0.375 moles is also in solution with whatever was made from our limiting reagent, which would be the conjugate base. We can then use the Henderson-Hasselbalch formula and plug in pH in our pKa and the log of base over acid, which we found from the number of moles in our solution. Again, this should be concentration that you're plugging in, but since we're dividing by the same volume to get to concentration, it's all going to work out. So then we end up with a pH of 2.92. Looking at the Henderson-Hasselbalch equation, your pKa is important here because that's going to tell you if your pH is equal to your pKa, that's your half equivalence point, and that's when your ratio of base to acid is the same, right? You have a 1-to-1 ratio. There's equal amounts of both. In this case, we have more acid than we do base, right? We have more acid, HNO2, than we do base, NO2. So our pH should still be lower than our pKa, right? We haven't reached that 1-to-1 ratio. We should still be in our acidic range in comparison to our pKa. Once we start making more base, we should be closer to that basic range past our pKa. But when the pH equals pKa, you have equal amounts of acid to base. That is your half equivalence point. That's for the equivalence point. At the half equivalence point, that's when you have an equal ratio of base to acid of your conjugate base to your weak acid in your buffer. That's for half equivalence. For equivalence, what you're talking about is when the moles of acid equal the moles of base. Yes. Yep, so you said that the moles of acid equal the moles of base at the equivalence point. That is correct. What I'm talking about is the half equivalence point, and that's when your moles of conjugate base is equal to your weak acid. And these are the same here in the Henderson-Hasselbalch. Those are 1-to-1, therefore making it log of 1, which is 0. So your pH equals your pKa, and that's the half equivalence. Yes. Yep, the weak components of the buffer equal each other at the half equivalence point. Andres, when? Okay. Correct. Yep. So this only applies when the strong base is not in excess. And that applies for, right, this is a weak acid, strong base. If you had the reverse, if you had a weak base, strong acid, right? If your strong acid is in excess, this is when this works, right? Your strong component of your titration, if that's in excess, then you use the Henderson-Hasselbalch equation. When we would have excess NaOH in this case, then that's when you just use straight up NaOH dissociation. So if we looked at this at a different time, right? This is 0.5. So same thing. I'm just going to copy this. Right, same thing, but now this time we'll say 1.25 liters of 0.5 molar NaOH has been added. Okay, when we look at this, again, the first thing we're going to do is convert to moles. So we have 1 liter times 0.5, we said this is 0.5 moles of HNO2. And then 1.25 times 0.5 is 0.625 moles of NaOH. Now in this case, this is an excess, this is your limiting reagent. Right? So now you're going to use up all of your weak acid and just have NaOH left. You will have 0.125 moles of NaOH in excess. Right? We just subtracted 0.625 minus 0.5. This is when it's important because now you need to take in volume into consideration. So you'll have 0.125 moles divided by 2.25 liters. And where did that come from? Where did the 2.25 liters come from? Perfect, right? We added our total volumes. So we get 0.056 molar NaOH. What does NaOH do? This completely dissociates into Na plus and OH minus. So all of this becomes the concentration for OH minus. So this becomes the negative log of OH minus. We know all of that concentration turns into concentration of our OH minus. Right, but that would be our POH. So then to get pH, we take 14 minus 1.25. Oops. So we get 12.75 equals our pH. Right, that's how you would be for excess strong or excess sodium hydroxide in this case. Okay, do we see the difference between the two and which one is in excess? Okay, any other questions on titrations? Does that answer some of the ones that came through in the chat? I will go look at your quiz for some voltaic cell ones. Okay. So for titration problems where you have to pick the best indicator, you want to look at your pKa of your acid or your base that you're working with. So in the case for what we were looking at with this most recent problem, right? You have a pKa of 3.4. You want an indicator that is in a range of about 3.4 or has a color change around 3.4. Somewhere that like grabs plus or minus 1 pKa. So anywhere from 2.4 to 3.4 to 4.4. If you have a range here, that's going to be a good indicator for that one because you're covering the buffering range of this certain buffer that you're looking at. Does that make sense? Let's do this. Unbalanced. Okay. Oh, sorry. Change in kilojoules per mole. Okay, so we're going to calculate the standard Gibbs free energy change in kilojoules per mole at 25 degrees Celsius for the following unbalanced redox reaction that takes place in a voltaic cell. But first, we're going to balance in a voltaic cell, and then I'll give you the rest of the question. Okay, so we're going to balance in a basic solution. So what does this mean we should see in our balanced reaction at the very end? Do you want to see H pluses or OH minus? Good, we want to be able to see OH minus, perfect. Okay, so, right, we're gonna split into our half reactions. We're gonna keep bromines together and we're going to keep nitrogens together. Okay, I just tend to go sideways. You can do them stepwise like I did in the notes first. But the first thing you want to do is balance your things that are not oxygen or hydrogen. So you want a 2 in front of bromine in order to make bromine 2 equal to bromine minus. You don't have any oxygens or hydrogens, so now you can just balance your charge with electrons. What is our charge? Where do we need to add electrons? Yep, we do have to do on the left side, and how many are we adding? Perfect, it is going to be on the left. How many? Perfect. All right, we'll be adding 2 electrons. So is this oxidation or reduction? This is your reduction. Perfect. Okay, then we're going to keep our nitrogens together. So we have N2H4. And this will go to N2. Our nitrogens are balanced. So what do we do in order to balance our hydrogens? Not yet. Oh, yeah, we do. That's fine, right? If we had any oxygens, we would be balancing with hydrogens first, but since we don't have oxygens, we can just jump straight to H plus. So where are we adding our H plus? Perfect. And how many are we adding? Perfect. Yep, we'll have 4 H plus. And then where are we adding our reactants this time? Reactants, electrons. Good. And how many? So is this our oxidation or reduction? Right, and that makes sense. We said that the first one was reduction, so our other half reaction should be oxidation. It looks like an oxidation reaction. We're good. All right, can we just add these up now? Nope. What do we need to do first? Good, we have to have the same number of electrons, so we're going to multiply our first one by 2. So we'll end up with 4 electrons, 2 Br2, and 4 Br minus. And then we can add them together. Okay, are we in a basic solution yet? Do we finish balancing our equation? Right, we need to add H plus, or H plus. We need to add OH minus to negate our H plus, and where are we adding that? Where and how many? Yep, we need 4H plus or OH minus on this side, or else also on our reactant side, right? Everything is balanced already, so we can't just add oxygens and hydrogens to one side. We do need to do this to both sides for our OH minus. These will form 4 water molecules since they're on the same side together, and then your 4 OH minus will hang out. So our overall reaction is 4 OH minus plus 2 bromine plus N2H4 goes to 4 Br minus, N2 gas, and 4 OH, sorry, 4 H2O. Okay, do we see how we did that in a basic solution? Any questions on balancing in a basic solution? Okay. So now we have yes. Yep. So when we added our 4H plus here, we have 4 additional positive charges on the right side. So we negate those 4 positive charges with 4 negative charges. Because then on the reactant side, we have a 0 charge. Yep, just like Coy explained. Okay, so to finish off our question, right, we're still trying to find the delta G of this equation. So we have 2 reduction potentials given to us. So and we're in an voltaic cell. So what are we going to do in order to find delta G? Yep, so we do know that delta G is equal to negative NF E naught cell. Do we have E naught cell? And if we don't, can we find it? Yep, so then we know that E naught cell is equal to E cathode minus E anode. Which one's our cathode, which one's our anode? Perfect. So this one is going to be our cathode. This one will be our anode. So we have E naught cell equal to 1.0693 minus negative 1.1628. We have E naught of the cell is equal to 2.23. Should our E cell be positive? Why should it be positive? I agree. Why should it be positive? Perfect. Yep. So we said in our question it's a voltaic cell, right? It should have a positive E cell then. What do we call something that has a negative E cell? Perfect. Yep, an electrolytic cell will have a negative E cell. Okay, so now that we found our E cell to be 2.23, we can use that in our delta G equation. Are we expecting delta G to have a positive or negative value? Good. It should be negative, right? Yes. Yep. Voltaic cells are spontaneous, and so something is spontaneous, it has a negative delta G. So we should end up with a negative delta G at the very end. N is our number of electrons transferred. How many electrons did we say were being transferred? 4. Perfect. Faraday's constant, I forgot. 96485. This is in joules per volts times mole. And then we have 2.23. So delta G should equal negative 861,456,457. This is in joules per mole. So in order to get to kilojoules, this will be negative 861.5 kilojoules per mole. Right, if you're off by 0.1, excuse me, if you're off by 0.1, then that should be good enough or close enough, I would say. Okay, does that help with the voltaic cells and the questions that came in with electrochemistry? Are there any other questions from electrochemistry that we wanted to look at? Yeah, of course. Galvanic and voltaic are the same. They will have the same setup, so they should both have a spontaneous reaction. They should both be positive. I believe you would want your metal to have a higher reduction potential. So then it would result in that metal forming the solid first or more easily. Um, I think that's how you would want to do it. Um, I don't think that's something you need to worry about for your exam. Um, but uh, but I do think you would want it to have a higher reduction potential. Yes, more positive, because you want it to be cathode minus anode. So you want a positive reduction potential. This one, no. If we're looking at this one here, it's okay that it's not balanced. It's probably given to you as the reduction potential not balanced, so that when you solve for the delta G, she makes you think about how many electrons are being transferred. Just because you have a multiple, like you're going to multiply this by 2, does not mean you double your reduction potential. Just think of it as like having 2 of those bromians going on at the same time, both producing the same number of volts. Does that make sense, Kingston? Great. Okay. Yeah, so a problem with effect on pH on solubility. So if we look at something like, oh, I don't know. Let's look at magnesium phosphate. Let's say this is, let's not say that. Let's say this is, hold on, let me think. Let me look at your solubility chart. I can't put the proper one. So if we have, let's say aluminum phosphate. Okay, this is going to be solid. So what would our KSP for this look like? How many ions of aluminum are we forming? How does this break apart? Into what ions? Yep, we have Al 3 plus and PO4 3 minus. And PO4 is given to you in your solubility chart. So if you forget, right, you can always reference that. See that it's 3 minus. We see that we have a 1-to-1 ratio. And then, so that means that aluminum has to be 3 plus. Okay, so these will be aqueous. These will be aqueous. So, right, in a solution, this would have a certain pH with water, whatever it is, blah, blah, blah. If we wanted to, in terms of solubility and things that you can do to increase solubility, you have to look at your ions that are in solution. If we were to add a strong acid, if we have a strong acid, that makes, let's say, HCl. That puts H plus and Cl minus ions in solution. Right? Would we agree? So now that we have these 4 ions in solution, we're going to look at, okay, what could happen now with these 4 ions in solution? We could have aluminum and hydrogen. Are those going to pair up? Do those form anything? Do 2 positive charges form a compound? Nope. Right, those don't pair up, but what about aluminum and chloride? What is that going to do? Those could pair up, but what do we form, right? If we form aluminum chloride, this is AlCl3. What kind of compound is that? Is that ionic or covalent? This will be an ionic compound. Perfect, right? This is ionic. Yep, so this is an ionic compound. You have a metal from aluminum and a nonmetal from chlorine. If they are ionic and you're in an aqueous solution, even if they pair up, they're going to pair up for a second and then immediately split apart again. All right, so they could pair up, but then they're going to dissociate. So aluminum and chloride will stay apart. We said that we could have a phosphorus or a phosphate and a chlorine pair up, but those are both negative. Those aren't going to compete, or those aren't going to pair up. What happens to hydrogen and PO4 3 minus though? What happens when we get here? What forms? Good. This forms H3PO4. Now you have H3PO4 in solution, right? You're in an aqueous environment. So what's going to happen with H3PO4? H3PO4 with water will now dissociate into H2PO4 minus and H3O plus. Do we agree that that's what's going to happen? Do we see why that's going to happen? Okay, so if we are going to pair up hydrogen and PO3 minus, and then we're going to form a like secondary reaction, right, where that new strong or that new weak acid is now going to form a buffer situation, what happens to our concentration of PO4 3 minus in solution? What happens to this concentration? Yeah, perfect, right? Since it's combining with the H3O plus, that is going to, right, form a complex of H3O-PO4 minus. It gets taken out of solution as a phosphate ion and forms a secondary reaction. So this concentration decreases. So how does that affect our equilibrium of our insoluble salt. If our ion is decreasing, what's going to happen to our salt? Does that increase its solubility or decrease its solubility? Yeah, it's going to increase solubility, right? Because when we interrupt equilibrium, product is being removed. If product is being removed, we're forming like a valley or a hole. We need to fill that, replace those ions that we took out of solution. And so we're going to form more products and we're going to increase our salt's solubility because while we're decreasing pH. And we decreased pH because we added strong acid and we're forming some of those H3O plus ions from the weak acid that we formed by combining H plus and PO4 3-. So in this case, as solubility, as pH decreases, solubility increases. Do we see how that's happening? Cool. Great. What other questions do we have about polyprotic and whatnot? Right, so if we keep on increasing, I would have to think about that as a general rule. I believe most insoluble salts tend to do that, because it's usually the anion that is pairing up with the H plus. So I would say as a general rule, yes. However, I would double check. I just can't think of an example right now where it wouldn't do that, where it wouldn't like increasing pH or decreasing pH would not increase solubility. So I think that is a correct general rule. But as you're practicing, make sure that the rule follows. I don't want to tell you a general rule and then it not be correct. Um, remember the quiz question you want us to choose what compound would increase solubility the most? Yes, I would say that a weak acid or a strong acid would probably increase solubility the most, for this reason that we just went over. Um, if it has some form in order to take ions out of solution to form an acid-base reaction, it's going to increase solubility. Because you will always be taking products out of solubility or out of solution and forming something else. So that equilibrium gets disturbed every time. If you're adding another salt, right, if we're adding, say, sodium chloride or aluminum chloride, right, usually that is increasing the ion concentration salts already, and that is pushing your equilibrium back towards the precipitate. Adding an acid or a base is I'll say adding an acid is usually decreasing pH and increasing solubility for your insoluble salts. Is that on quiz 5 or 4? Do you remember? I can look. Okay. Okay, so the question I'm seeing is, is this the, is this the question we're thinking of? Okay, so there are these choices. So with these choices, right, these are all salts, they're all ionic compounds. You want to break these up into ions. Right, so as we're looking at these, we're saying that we're in a strong acid. Right, so a strong acid, whatever that may be, I always just think of HCl first, right? That will always completely dissociate into H plus and Cl minus. The strong acid component that we care about is the H plus. So if we say, okay, let's take our H plus and pair it up with NO3, that would form HNO3. That's a strong acid. That strong acid completely dissociates. It's not going to take any ions out of solution, not going to do anything. Pair up H plus with I minus. That forms HI. That's a strong acid. That's going to completely dissociate, not taking any ions out of solution, doesn't change solubility. HCl, H plus and HCl and Cl minus form HCl. That's a strong acid, completely dissociates, doesn't change solubility. HF, HF is now a weak acid. This weak acid will go into a new solution or a new side reaction, forming an equilibrium, taking some ions of F minus out of solution, therefore disrupting solubility and forcing more of that calcium fluoride to dissolve or increase solubility in that acid solution. So it has to be a weak acid because that will form a complex. If it's a strong acid, then it will stay completely dissociated and it's not taking any ions out of solution. Perfect. Alrighty. Well, it's 6:06, so I will wrap it up for today. Thank you for coming. And yes, so the answer is SAFO2. SAF2. CAF2. Yep. Yeah, thanks so much. So thank you so much, everyone, for coming. If I don't see you on Zoom again, just thanks for being in great class, and I'll see you on the final on Monday. And if not, I will see you probably at 1 p.m. on Sunday for just last minute questions. And I should be prepping just a couple extra review questions for y'all just for additional stuff, and the mock exam is not enough. So just be on the lookout for that and then look out for a Zoom link for Sunday. Thank y'all, and let me know if you need anything in the meantime. Good luck.